All right, today we're going to finish up chapter 5 and start on chapter 6. All right, we left off with the collecting over water. So I want to do one example of collecting over water. All right. So anytime you hear the term collected over water, that means that your gas also has water vapor. All right, so collecting gas over water. All right, so we had our pressure. When we do our lab tomorrow, we're going to have the pressure total, which is our lab pressure. And that's going to equal the pressure for tomorrow. We're collecting oxygen plus the pressure of water. And again, on table 5.6, that's where you're going to find your pressure of water. I am going to post the pressure of the day on the board. You will look up your pressure of water from table 5.6 and your temperature that you will read on your thermometer. Then you see the math here is you take your total pressure minus the pressure of water, and that's going to equal your pressure of your oxygen gas. Note that the pressure that I'm going to give is the same one that's going to be from the Quincy Airport, which is the let's say it's 29.92. That's what they say that the barometric pressure is. And of course, that is in inches of mercury. You will have to convert that to millimeters of mercury, and then eventually you'll have to get to atmospheres, for PV is equal to nRT. All right, so the number that you always get for barometric pressure in the United States is in inches of mercury. Then you know that there are 2.54 centimeters equal to 1 inch. And you know that there are 10 millimeters in 1 centimeter. And so when you do this conversion, it comes out to be 760.0 millimeters of mercury. And that is equal to 1.000 ATM. All right, so you can use that as a conversion, and it's easy to remember because it's written the same forward and backward. So 29.92 inches of mercury is equal to 1 atmosphere. You don't have to memorize that, but that would be very helpful when you are converting your inches of mercury into atmospheres. All right, so if the pressure of the day turns out to be 769 and your thermometer in the lab reads 19 degrees Celsius, you go to table 5.6, you find the 19 degrees Celsius, and you find the vapor pressure of water at 19 degrees Celsius. All right, and so then you put in your pressure total, you put in your pressure of water, you subtract the total from the pressure of water, so you subtract the total from the pressure of water to get your pressure of your gas, and in this example, the gas was hydrogen. All right, so note that your vapor pressure goes up as you heat as the room gets hotter and hotter and hotter until you're at the boiling point where it is all vaporized into the atmospheric pressure of 760 millimeters of mercury. All right, but that table will be given for this test. So you will have to realize that when it says collected over water and you want the pressure of your gas, they're not giving you the pressure of your gas, they're giving you the pressure total. You have to subtract your pressure of water. To get the pressure of your gas, you take the pressure total, the given pressure, and subtract the pressure of water. All right, so here's another example. All right, so you read this. If you do not see the collected over water, you will get the pressure wrong, which gives you the wrong answer. It gives you the answer that is close, but it is the wrong answer. All right, so you're looking for that phrase. You're collecting a gas over water, and you're collecting nitrogen. That means our total pressure is going to equal the pressure of nitrogen plus the pressure of water. And so to get the pressure of nitrogen, the gas, we have to take the pressure total, subtract the pressure of water, and that will give us our pressure of nitrogen. All right, and so when you want to know how many liters of nitrogen you would obtain, all right, so you have to have PV is equal to nRT. And so it is the pressure of oxygen, volume of oxygen, moles of oxygen, temperature of oxygen. R is a constant. Oxygen, we're not doing nitrogen. Okay. It is the pressure of nitrogen, volume of nitrogen, moles of nitrogen, temperature of nitrogen. In lab tomorrow, we are doing oxygen. This problem is nitrogen. All right, note that the only gas in this equation is the nitrogen gas. You cannot use volume ratios. You can only use mole ratios. All right, so what you're going to do is you're going to take your 5.68 grams of your ch4NO2 and not use PV is equal to nRT because this is not a gas. Not a gas. It is labeled for you, solid. You don't have to know that's a solid. It will be labeled for you. What that means is if you use PV is equal to nRT, you will get the wrong answer. Do not use PV is equal to nRT unless you have a gas. You can't use it here. You can use it here. You cannot use it here. You can only use it for a gas. It's an ideal gas equation. All right, so you have your 5.68 grams of your NH4NO2. All right, you convert that to moles. So grams per mole. This is your molar mass from the periodic table. You have two N's, that's 28.02. You got four H's, that's 4.04. You got two O's, that's 32. All right, so that gives you 64.06. So we put in our 64.06. All right, so that's moles of our NH4NO2. And we got moles so that we can do the mole ratio. And this one happens to be a 1-to-1. 1 mole of your NH4NO2 gives 1 mole of nitrogen gas. And so this is how we find the moles of nitrogen. This is the total pressure. We look up our chart at 23 degrees Celsius. So if we go back and we look at 23 degrees Celsius, we get a 21.1. So now we know 21.1 millimeters of mercury at 23 degrees Celsius because that's on table 5.6. And so our pressure of nitrogen is our pressure total, 727 minus 21.1, and that gives us 706 millimeters of mercury. All right, so there's our pressure of nitrogen. Here is our moles of nitrogen. All right, so we need the temperature. That's 23, but we can't use Celsius, 273. So our temperature is 296 Kelvin. All right, and then R is a constant, so we have everything we need. So we want the volume. Volume is nRT over P. We have moles, we have temperature, we have pressure. We do have to get our pressure in the right units. So we take our 706 millimeters of mercury and divide by 760 millimeters of mercury in 1 ATM. All right, so the moles is in moles. R is the 0.08206. Temperature in Kelvin, pressure in atmospheres, and then we just push the buttons and we get our answer. All right, so when we push the button for moles, all right, so it should be to 3 sig figs here, 0.889 moles of nitrogen. Okay, we have our 296 already. We did not get a number for our atmospheres, so we got to convert our pressure into atmospheres. They don't give a number for it either. All right, they just say that we're going to convert it within the problem. And then you push the buttons. Why did they make that a 7? All right, well, let's see. One of these is wrong. Let's figure out which one. 5.68 divided by 64.0. They have, and that is, yeah, this is wrong. Okay. They have an extra 8 in there. So the answer is 0.887 when you push the buttons on your calculator. That is wait a minute, 5.68 divided by 64.04. That is actually 0.08. I really messed that one up. All right, so this is right, but when you push the buttons on your calculator, you get a 0.0887 moles. All right, 0.0887 moles. Now they have it right here. So then you go to the next page and they do have the correct number of moles. All right, and so when you push the buttons here, you will get your answer of 2.32 liters of nitrogen gas. All right, so the key part here, most people will get everything right except for the pressure. So make sure when it says collected over water, you don't give the total pressure. You give the pressure of the gas. You take the total pressure minus the pressure of water. All right. So next topic for chapter 5 is the kinetic molecular theory. All right, so we're going to talk about kinetic energy, the energy of motion. All right, so EK is equal to kinetic energy. It used to be KE, so if you see KE, that is kinetic energy. If you see EK, that is kinetic energy. And that is 1/2 mv squared. Now, mass, we want to use the SI unit for mass, so we want the mass in kilograms. Velocity is going to be a speed. That is going to be in meters per second. And when you take kilograms times meters per second squared, you get units that are kilogram meter squared per second squared. And that is a joule. All right, so you need to know that a kilogram meter squared per second squared, that is the SI unit for energy, which is the joule. All right, so postulates of the kinetic theory. Gases are composed of molecules whose sizes are negligible. They're very small. And so when they're in a 1 liter flask, they take up such a tiny amount of space that we say that that is a negligible amount of space. Molecules move randomly in straight lines in all directions at various speeds. The force of attraction and repulsion between two molecules, the intermolecular forces. And a gas are very weak, except when the molecules collide. So unless they hit each other, they don't know they're there. When molecules collide, the collisions are elastic. You don't lose any energy. You have an elastic collision. The average kinetic energy of a molecule is proportional to the absolute temperature. That, of course, means the temperature in Kelvin. All right, so the higher the temperature, the faster they're going to be moving. The lower the temperature, the slower they're going to be moving. All right, elastic collisions. Yeah, okay, whatever. Fine. Ideal gas law. Yes. Average force, frequency of collisions. Okay, we have, all right, so molecular speeds. So we want to calculate how fast the molecules are going. All right, so again, the higher the temperature, the higher the speed. It is a direct proportionality. You make the Higher temperature, you get the molecules to move faster. We can actually calculate the speed on average of a molecule by this equation right here. Now, this is where things are getting a little difficult because we have R. R is equal to 8.314 joules per mole Kelvin. Is that the same as the 0.08206? Yes, it is exactly the same. Is it the same units? No, that's why there's a different number. That's like saying 1,000 milliliters is the same as a liter. Yes. All right. A little bit different, but similar. All right. But we have the R value. That's the ideal gas constant. But these are the units that we need for this R value. All right. Because we're going to do the units. All right. So R. We're going to use joules, but in the last slide, we saw that joules, that was a kilogram meter squared per second squared. And that's what I want to use for my units here. R value, kilogram meter squared per second squared. The temperature, always in Kelvin. If you have T and you don't have Kelvin, you have the wrong answer. And then you have your well, that's per mole Kelvin, sorry. Per mole Kelvin. All right, so the joules, that is the kilogram meter squared per second squared, and you're still per mole Kelvin here, so that the Kelvin here cancels Kelvin here. Molar mass, this one also has to be in the SI units. The SI units for molar mass, you have to put it in the SI units, which is different. You've not done this. Because what is the molar mass? Well, it is the mass divided by the moles. All right, except the SI unit for mass is not gram, it is kilogram. So it has to be in kilograms per mole. That is the main reason why people miss this, because they do not put the molar mass in this equation in the SI units, which is kilograms per mole. So the moles cancel, and now the kilograms cancel. If you don't have it in kilograms, the kilograms will not cancel the kilograms. All right, and note that this is a square root. So you end up with meters squared per second squared, then you take the square root and you get meters per second. And that is your root mean square speed. All right, this equation is going to be given, but if you don't know what R value to use and you don't know to use the SI units for molar mass, it doesn't matter if you have the equation or not, you're going to get the wrong answer. So make sure you know what units you need in order to get the unit of meters per second. Because a liter atmosphere is never going to give you the unit meter per second. A joule, again, you have to know that a joule is a kilogram meter squared per second squared. You need to know that. The easiest way to know that is to go to the kinetic energy equation. All right, so most of you, if not, you will see this many times. The kinetic energy, E sub k, is equal to 1/2 mv squared. Many people already know this. All right, what they don't know is the mass SI unit is kilograms, so make sure you know that. And then velocity is the speed, it's meters per second. And when you square it, you get a kilogram meter squared per second square. And the energy units that we use are joules, the SI unit for energy. All right. Again, yes, so this is the main reason why people miss that. The second main reason why people miss it is to use the wrong R value. Third main reason why people use it, and I am not lenient at all, they do not convert their temperature to Kelvin. All right, so what is the RMS speed of carbon dioxide molecules in a container at 23 degrees Celsius? So you have your equation, 3RT over the molar mass. And so you have your square root of 3, then 8.314. You have to use the right R value. Temperature, you add 273. You have 296 Kelvin. It has to be in Kelvin. And then here is the part that most people will miss, because they'll get CO2. CO2, that's 12.01 and 32. I got 44.01. They put in 44.01 and they have the wrong answer. All right, this is grams per mole. You have to know that your SI unit for molar mass has to go in here. And so you have 1,000 grams in a kilogram. All right, so this is a 0.04401 kilogram per mole. That is the only way to get the units of meters per second. So we just did the units. That's a kilogram meter squared per second squared divided by mole Kelvin. That's the units for R. The units for T, Kelvin. The kelvins will cancel. And now the molar mass has to be in kilograms per mole so that the kilograms cancel the kilograms and the moles cancel. And when we get our answer, we have to take the square root. And when you take the square root of meters squared per second squared, you get the units for speed. All right, so the root mean square speed. Again, the equation is given, but if you don't know how to put in your R value, it has to be the 8.314 temperature. Most everybody gets that right. They put that to Kelvin. Not everybody, but most everybody. Molar mass is the main error in solving this problem. This problem is very simple, but if you don't pay attention to units, it's impossible. And when you push the buttons, you get a 410 meters per second. So you wouldn't have to put that in scientific notation, 410 meters per second. Or put it in scientific notation, it doesn't matter. All right, so if you increase the temperature, if you had a higher temperature, 296, you're going to get a larger speed. If you had a smaller temperature, you're going to get a slower speed. Molecules move faster when the temperature is higher. All right, so diffusion. All right, so we're going to have diffusion and effusion. All right, so the smell coming out of that lab, the gases are diffusing throughout this room. All right, so you're eventually going to smell that odor. All right, now that is diffusion. When you have effusion, that is when the gas is going through a small hole. All right, so you can either have a very small hole in a balloon. You can have, normally what we do is we have a foil over, so you have your gas in here, and then we poke a little pinhole in the foil, and we get the rate of the gas effusion, fusing through a small hole. So this is the gas that flows through a small hole in a container. All right, so then we have our equation for Graham's law of effusion. And so we are going to see that the smaller gas molecules are going to effuse faster than the large gas molecules, given that they are at the same temperature. So at constant temperature, we are going to find, and pressure, so same temperature, same pressure, we're going to look at the rate of effusion. And again, it is all based on the molar mass. So the smaller molecules of gas will effuse faster than the larger molecules. All right, so both hydrogen and helium have been used as buoyant gases in blimps. If a small leak were to occur, which gas would effuse more rapidly and by what factor? All right, so you have hydrogen, which has a molar mass of 2.02 grams per mole. You have helium that has a molar mass of 4 grams per mole, 4.00 grams per mole. All right, and so the hydrogen would effuse much faster. To find that factor, you have to take the ratio of the square roots. All right, and so it is not twice as fast, it is the square root of 2 times as fast. All right, so you have, it is 1.4 times as fast. So you take that, the reason why hydrogen is going to go faster is because the molar mass is smaller. The smaller gas molecule is going to effuse through a small hole faster than a larger gas molecule. All right, and so your hydrogen, and that's all based on the molar mass, is going to go faster out the hole than helium. All right, and so then you have that as the square root of the ratio of molar masses. All right, so the equation that is going to be given on the test for Graham's law of effusion, make sure I have the right equation. All right, so it's going to be, this is going to be the equation. Z effusion. So Z is the rate of effusion of gas 1 divided by the rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. All right, and so it doesn't matter which one you put on top, but it does matter on how you say it. All right, so you need to know that the smaller molar mass is going to have a faster effusion rate. Smaller molar mass is going to be faster through the small hole. All right, and so you want to know what factor that is going to be of. So your rate of effusion of your hydrogen, all right, so this is the rate of effusion of hydrogen compared to the rate of effusion of helium, is equal to the square root of 4.00 over 2.02. And now, why doesn't this have to be in kilograms per mole? You can have any units you want as long as you have the same on top and bottom. So if you want to go to kilograms per mole, you will get the right answer. You wouldn't have to do that because grams per mole cancel grams per mole. It's all about the units that have to cancel. And so this will then tell you that you have the rate of effusion of hydrogen is 1.4 times faster than the rate of effusion of helium. So you can actually multiply both sides by the effusion rate of helium. So you have the effusion rate of hydrogen is 1.4 times the effusion rate of helium. All right, so helium is slower by a factor of 1.4. All right, so this is the equation. All right, but you will also need to know how do you calculate the effusion rate? What we're looking at is volume over time. Volume over time. This is volume of gas 1, time of gas 1 versus volume of gas 2, time of gas 2. So your Z effusion is your volume per time. V is equal to volume, and T is equal to time. All right? And so when you're dividing them, that is a lowercase t. That is not an uppercase T. This is at constant temperature and pressure. All of the effusion rates are going to be at constant temperature and pressure, always. Every effusion rate that you're going to see is constant temperature and pressure. This is a lowercase t. Lowercase t is time. Uppercase T is temperature. All right, so the units of volume, they just have to be the same. It doesn't make any difference what the units are. Time, same. It doesn't matter if you're using hours, days, minutes, seconds. Volume, liters, decimeters cubed, meters cubed, it makes no difference, but they have to be the same on top and bottom so that they will cancel. All right, so when you're doing your effusions, it is about the volume of gas escaping per time. All right, we're going to do one real gas equation, and that is going to be the van der Waals. There's a few others, but the van der Waals equation is the one that we are going to use. All right, so an ideal gas, no gas is ideal. All right, so we have real gases that do not behave ideally. All right, and so we have one, it is the van der Waals equation, and this equation is going to be given to you. All right, so here's the equation for the van der Waals equation. All right, so the volume term becomes volume minus NB, and your pressure term becomes pressure plus N squared A over V squared. So you have these two new factors, and they are A and B for a given gas. And those are found on table 5.7. All right. So the A and the B factors are there for the deviations from your ideal behavior, which are molecules do take up some space, and the molecules do have some interaction even if they don't collide. So the two factors that they're taking into account is that gas molecule, even though it doesn't run into it, still knows it's there, and the volume of that gas is not 0. All right, so here would be a problem. Use the Van der Waals equation to calculate the pressure exerted by 2 moles of CO2 that has a volume of 10 liters. So they give us moles, they give us the volume, and they give us the temperature. And they want the pressure. All right, and compare this value with the pressure obtained from the ideal gas law. So the first thing you're going to do is you're going to say, I need A and B. So you got to find A and you got to find B. It tells you the gas. The gas is CO2. And so you got to go to table 5.7 and find the values for A and B. All right, and so for this is going to be table 5.7. All right, so table 5.7 is going to be given to you. You find CO2, you find A, there's the number. You find B, there's the number. All right, you have your N is in moles, yes. Volumes in liters, yes. Temperature is always given in Celsius. You never use Celsius. You convert that to Kelvin. Now you have everything you need. You just plug all these numbers into your equation. All right, first we're going to do the easy one, and that's PV is equal to nRT. All right, so we plug those numbers into PV is equal to nRT, we get our answer. All right, so the pressure using PV is equal to nRT, we get 4.89 atmospheres. All right, so then we're going to put it into the real gas equation. All right, and so you don't have to solve for P. You could leave it the way it is as P plus N squared A over V squared. The main reason why this problem is missed is not for anything but math. The mathematics of this equation is not simple. And that's equal to nRT. So the equation that is given and will be given on the test is here. And so you're going to have to solve for P. What I would highly recommend doing, unless it's multiple choice and it doesn't matter, when it says show all your work, I would leave it just as written, and I would plug in all the numbers. You put in 2 for N, you square it, you put in your A value, you put that in here, you put in your V, that's 10, you square it, you put in your V, that's 10, you put in your N, that's 2, you put in your B, that's given over here, you put in your N, that's 2, do not miss it for the wrong R value. All right, so we're doing a gas law. In an ideal gas law, there's only one R value we ever use. We're using the 0.08206 liter atmosphere per mole Kelvin. If you use the joules per mole, you'll never get a pressure unit. All right, you're going to get a speed, and that is not what we're looking for. We're looking for a pressure unit. We have to have the R value that has the atmospheres. All right, because when you try to solve this, you have to be very good at math. All right, the way they solve it is you're multiplying these two things, all right, on the left side that have parentheses. So you have to divide both sides by V minus NB. I would not try this unless you are really good at math. V minus NB. Then we have to get P all by itself. So now we have an addition on this side, and so we have to subtract N squared A over V squared on both sides. Again, I highly recommend just leaving the equation the way it is and plug in all your numbers. And then if you screw it up, at least I know that you had it all set up and you just messed up on your calculator. All right, so when you push the buttons, you're going to get atmospheres, and that is 4.79. All right, so 4.79 ATM. What do we have before? 4.85. Well, I got to back and look. The ideal gas equation, 4.89. 4.89. All right, so what we're going to do now is we're going to see what the error is from using PV is equal to nRT. All right, so this is ideal, and this is real. All right, so what we would do here when we have our two numbers is to find the percent error. And that is your actual minus theoretical divided by theoretical times 100. All right, so what we got actually, so the estimated, the lab amount, all right, so that's what we got, and that was the ideal. So this is ideal versus reals. Real's the correct answer, all right, so over real. All right, so ideal 4.89 minus 4.79 divided by 4.79 times 100. And so that will give us our error for using the ideal gas equation instead of using a real gas equation. All right, so when we do that, we get 0.10 and divide by 4.79 times 100, we get a 2.1% error. All right, and that is an acceptable error. And so we pretty much stick with the ideal gas unless you have to be closer than a 2% error. If a 2% error is not acceptable in your research, then you would have to do the real gas equations. But the ideal gas is sufficient for most calculations. I don't know if they do an error analysis. No, they don't. All right. So that is the end of chapter 5. All right, chapter 6. All right, so chapter 6 is thermodynamics. All right, so we have thermodynamics. And so now we're going to talk about endothermic, exothermic. We're going to talk about heat. And so we're going to have reactions that absorb heat, reactions that release heat. All right, and so we're going to talk about the relationship between heat and other forms of energy. That's thermodynamics. When we do thermochemistry, all right, so that is thermodynamics that is concerned with the study of heat absorbed or evolved by a chemical reaction. All right, so we're going to talk about endothermic, that is heat absorbed, and we're going to talk about exothermic, and that is heat evolved or heat released in a given chemical reaction. All right. So energy, the potential or capacity to move matter. One form of energy can be converted to another form of energy. You got electromagnetic, you got mechanical, electrical, chemical. All right, so we're going to talk about the difference between kinetic energy. We just did kinetic energy, E sub K or Ke, and that is 1/2 mv squared. And that is where things are moving. They have a speed, they have a velocity, they're moving, all right? Then you've got your potential energy, and that is the energy of position and also your internal energy. All right, so again, remember you have to have the SI units. That mass has to be kilogram, velocity meters per second. And remember always that a kilogram meter squared per second squared, because you have to square the velocity. You need to know that that is the SI unit for energy, which is the joule. That is the only unit for energy. Well, we're going to talk about calories, but we almost exclusively work with joules. All right, and so here is the joule. All right, the joule is J, it's kilogram meter squared per second squared. All right, so if we have calories and we want to have the SI unit joule, you will be given this conversion factor. All right, you don't have to memorize this conversion factor. you will have that 1 calorie is equal to 4.184 joules. That is an exact, that's an infinite number of significant figures. That is not going to determine how many sig figs you give in your answer. All right, so the calorie, it took a while to get rid of calories and go to joules in chemistry, but pretty much they have gotten rid of the calorie. When I took chemistry, everything was in calories, nothing was in joules, and now it's the opposite. Everything's in joules and hardly anything's in calories, but the definitions were very nice. All right, so the definition of a calorie, all right, it is the energy required to raise the temperature of 1 gram of water, 1 degree Celsius. So that was a very nice definition of a calorie. All right, so we want kinetic energy. So remember, kinetic energy, that's equal to E sub K. That is equal to 1/2 mv squared. All right, so we need to have our mass. It has to be in kilograms. So 1/2 of 75 kilograms. And then we have to have our velocity in meters per second, 1.78 meters per second. And we square that. And now we have a kilogram, meter square per second square, and we have a joule. All right, so this would be a very simple question. It would be a lot harder if they gave it here and they gave it here, and you had to convert to the correct units. All right, and everything is given to 3 sig figs. You give your answer to 3 sig figs, and you would have 119 joules of energy. All right, your potential energy. All right, so that is the energy virtue of its position. All right. So when you have a dam, you have a lot of potential energy. The water is, above the dam, and then when they open the dam, now the water is moving. So potential energy converted to kinetic energy. So you have potential energy. The higher it is, the more potential energy it has. All right, and that's why you have an H here. The more of it you have, the more it weighs. The higher the potential energy. That's the mass value. All right. And so M is your mass. And again, SI units, it has to be in kilograms. All right. Gravitational constant is going to be given to you. You don't have to memorize the acceleration due to gravity. That is going to be given. 9.80 meters per second squared. And then your height has to be in the SI unit of meters. So the mass may be given in any units. You got to convert it to kilograms. Height can be in any units. You got to convert it to meters. Gravity is going to be given to you in the correct units. All right, and so all you need to know is how much does it weigh and what's its mass and how high up is it. And from that, you can calculate the potential energy. And now the units. All right, so again, you got your kilogram, you got your meters per second squared. So you got your kilogram, you got your meters per second squared, and you got your meters. All right, so we see we have a kilogram, meter squared per second squared. Again, we have joules. Whatever energy that we're going to have, the equation is going to work out to give us joules. Again, you have to know that's a kilogram, meter squared per second squared. All right, so then you have an internal energy. So when you have the sum of kinetic and potential energies, the particles making up the substance, all right, so your total energy total is kinetic plus potential plus your internal energy, which has the symbol U. All right, so you have the law of conservation of mass. Then you also have the law of conservation of energy because we have Einstein's equation, E is equal to mc squared. All right, so c is the speed of light. That's a constant. All right, so your mass and your energy have both a conservation. So we have the conservation of mass, which means we have the conservation of energy. All right, now this is only true when you do a chemical reaction. A nuclear reaction does not have a conservation of mass, and it does not have a conservation of energy. All right, so energy may be converted from one form to another, but the total quantity of energy remains constant. All right, thermodynamic system. So we're going to talk about a system. All right, so the system is where the reaction is occurring. So here is the reaction. This is an endothermic reaction. All right, you mix it up, it gets very cold. If you have the bottom of it wet and you put it on a board, it will freeze to the board. All right, so this is your system. Anything that the system is next to is called the surroundings. And so you have surroundings here. You got surroundings here. You got surroundings here. All right, anything, you have surroundings here. Anything that surrounds it, you have the system, and everything around it is called its surroundings. All right, so we're going to talk about the heat, and the symbol for heat is Q, and the energy is either going to flow into or out of a system. All right, and that is due to a difference in temperature. All right, so key here is that the heat flows from higher temperature to lower temperature. All right, so the heat flows from a higher temperature to a lower temperature. Q is defined as positive if the heat is absorbed. And you will be able to tell that in the last picture. It is an endothermic reaction. It is very cold. All right, so Q is positive if the heat is absorbed. If the heat is absorbed by the system, you feel it. It is very cold. All right, if you have Q that is negative, now heat is released. Heat is evolved. If you add your sodium chloride in your HCl, your sodium hydroxide in your HCl, and that gets very hot, that is what's happening. You have a exothermic reaction. You have a negative Q. Heat is evolved. You know that because the flask is now hot. So if you mix two things together and it gets hot, then you know heat is evolved. If you mix two things together and it gets cold, like a cold pack, you break and it gets cold, that is heat absorbed. That is an endothermic reaction. All right, so when we're talking about a reaction, this would be called endothermic, and this one would be called exothermic. Endothermics get cold. Exothermics get hot. So you can tell if it is endothermic just by touching the flask. If it's cold, it's endothermic, heat is absorbed. If it is hot, it is exothermic, heat is evolved or released. All right, so now we're going to talk about the heat of a reaction. So I keep talking about chemical reactions. All right, so the heat of the reaction is not just Q. The heat of the reaction is delta H. And you get delta H by taking Q divided by N. All right, so that's the heat divided by the moles. All right, moles is never negative. Moles is always a positive number. So if your Q is negative, your delta H is negative. If your Q is positive, your delta H is positive. All right, I keep talking about endothermic and exothermic. Here it is, endothermic process, a chemical reaction or process where heat is absorbed. All right, so your Q is positive. And again, if you touch the reaction vessel, it will feel cold. Exothermic. All right, so your heat is evolved, heat is released. Q is negative. The reaction will feel warm. So you can just touch it. If it's cold, it's endothermic. If it is hot, it is exothermic. If it is neither, then it's going to be slightly one or the other. You can't tell if the temperature doesn't change at all. All right, so again, there's going to be lots of questions on endothermic and exothermic. Endothermic, reaction vessel cools, heat is absorbed, energy is added to the system, Q is positive. Exothermic, it is warm, feels warm, heat is evolved, energy is subtracted from the system. Q is negative. Make sure you know endothermic and exothermic. All right, so enthalpy, that is your H. Okay, so I talked about delta H. Delta H is equal to the heat of reaction. All right, and so it is going to be negative if it's exothermic. It is going to be positive if it is endothermic. All right, and so this is going to be used to obtain the heat absorbed or evolved in a chemical reaction. All right, because it is per mole. You have your balanced chemical reaction, you have your mole ratio. We can find out exactly how much heat is going to be released or evolved in a given reaction, given an amount of reactant used. Extensive property, a property that depends only on the amount of substance. All right, so mass and volume are extensive properties. Density is not. It doesn't matter how much water you have. The density of water is 1.00 gram per milliliter. You can have a ton of it. You can have a drop of it. It's the same. All right. So an extensive property is one that depends on the amount of substance. All right. So mass. All right. So it matters how much you have. Volume matters how much you have. These are extensive properties. But density, boiling point, melting point, these are not extensive, they are intensive properties. All right, so state function. All it means by a state function is it depends only on where it starts, the present state, where it starts, and where it finishes. All right, which is then determined system that only depends on its present state. All right, so state function, it only depends on where it starts and where it ends. It makes no difference how it gets there. So a state function, you will know a state function because it's going to have a delta in front of it. So delta H, it's going to be the delta H products minus delta H reactants. All right, so it's the products minus reactants. It is final minus initial. So delta just means final minus initial. When you're doing a reaction, the final, that's your product. The initial, that's your reactants. If you want a delta T, change in temperature, that is your temperature final minus temperature initial. So it's always final minus initial. In a reaction, products minus reactants. All right, so the altitude of a campsite is a state function. All right, so it doesn't matter if you go to the left, which is more direct, or if you go in this, I don't want to walk straight up a mountain. I kind of want to go sideways up the mountain and then eventually get there. All right, so work is not a state function. All right, so when you're traveling a lot longer, you're going to do a lot more work than going directly to the campsite. But if you are a state function, which is your altitude, it doesn't matter which way. Heck, you could have went around the mountain 5 times and up to the top. It only matters where you start at the bottom and where you ended at the top. That is a state function. All right, so we're going to talk about heat of reaction or enthalpy of reaction. That is your heat of reaction. Again, you're going to have your delta H, and that's going to be your products minus reactants, right? Final minus initial. All right, your enthalpy change is equal to the heat of reaction at constant pressure. And so at constant pressure, which we're going to do most of our problems are going to be in the lab, everything is at the same pressure, we're not changing the pressure, then your delta H is equal to the Q value. All right, so we have a reaction. We add sodium to water, and you get sodium hydroxide and hydrogen gas. All right, so to find your delta H for this reaction, you're going to take off of table 6 point something, 6.1, 6.2, and you're going to take the delta H of your products, NaOH aqueous, H2 gas, products minus the delta H of your reactants, sodium and H2O liquid. All right, and what you're going to find is you're going to find that you're going to have a delta H that has a negative value. Products minus reactants, you add them up, and is going to be a negative 368.6 kilojoules. All right, so when you get a negative number, that means exothermic. So delta H is negative, then it is exothermic. Heat is released. All right. When you have your enthalpy and internal energy, you have this factor of PV. So your delta H is your delta U plus delta PV. And so your negative P delta V is the energy needed to change volume against an atmospheric pressure P. All right, so this is your pressure volume work. And so all of these equations will be given. You do not have to memorize any of these equations. PV is equal to nRT is not given, but these will be given. All right, so when we talk about work, work is equal to negative P delta V. All right, so work is going to be moving this piston up and down. All right, so the hydrogen gas had to work to raise the piston. All right, so for this reaction at 1 atmosphere, all right, so if we had 1 atmosphere, negative P delta V was equal to negative 2.5 kilojoules. All right, so to get that change in volume, they don't tell you what that volume is. All right, so negative P delta V, negative 2.5 kilojoules. They just give you that answer. All right, so you have your 268.6 kilojoules of heat are evolved. All right, so you have work anytime you are having a change in volume. So when you are making a gas, so here's your sodium, here's your water. The product is a gas, all right? So it's making hydrogen gas. That gas is going to push the piston up, all right? And so that is going to be a change in volume. The volume was initially wherever the water was. Now the gas is pushed that piston up, and that is a work. That is an amount of work, which is negative P delta V for your work. All right, so this is what we're going to do mostly on the test, and that is a thermochemical equation. There will be a number of these on the test. You're going to be given a reaction. It's going to be then give the thermochemical equation. So what you have to do is you take your NaOH number, you're going to find your delta H for this reaction, and that is going to be the delta H of your products minus delta H of your reactants. All right, so you got 2 moles of NaOH plus 1 mole of hydrogen gas. You add those numbers up, you got 2 moles of sodium, you got 2 moles of water, you add those numbers up, you take your product number minus the reactant number, and you'll get a delta H value of negative 368.6 kilojoules. Now, the thermochemical equation means you write the balanced equation, and then you write a semicolon. You can't see it now that I've got red all over it. And then you write the delta H value. All right, and so now you know that this is exothermic. All right, another way you could do it, but would not be proper, is to say that this is releasing your 368.6 kilojoules. All right, so that means that heat is a product. So you would then, the products would be, you would have 368.6 kilojoules plus 2 NaOH plus H2 gas. All right. If you had endothermic, then your heat would be on the reactant side. All right, so again, to get these numbers, we need a table. So we need table 6.1 or 2. Should be coming up real soon. All right, so sulfur burns in air to produce sulfur dioxide, S8. Burns in air to give SO2. To balance that, we need 8 of these and we need 8 of these. All right, so the reaction evolves, gives off exothermic. All right, so this is exothermic. When you see the word evolves or releases, gives off, that is exothermic. Per gram of sulfur at constant pressure, write the thermochemical equation. All right, now your delta H is Q over N. All right, so to find your delta H, you need the Q divided by N, which is moles. We have the Q value. You have to see that this says evolved, and so you have to know that Q is negative 9.31 kilojoules. But that is not per mole, that is per gram of sulfur. And so you have 1 gram of sulfur, and then you need the periodic table, 32.06, I do believe, is sulfur. 32.07 maybe. All right. All right, so we don't want per gram, we want per mole. 32.07 grams per mole. And now we have our delta H. To write it as a thermochemical equation, you put a semicolon and then you put that number. And then you put the delta H is negative, and then whatever you get for this, 9. We need how many sig figs? 3 sig figs, and that would be 299, negative 299 kilojoules per mole. So this is 299 kilojoules per mole. That is your delta H. So you write the balanced chemical reaction, and then you write the delta H after that balanced chemical equation. Oh, yes. Times 8. I'm sorry. That is not S. That is S8. So times 8. So that is 2.39. Negative 2.39 times 10 to the third kilojoules per mole. Negative 2.39 times 10 to the third kilojoules per mole. All right, so that is not just sulfur, that is S8. So the other answer, if it wasn't S8 that they gave you, if it was S plus O2 gives SO2, then the delta H for that would be negative 299 kilojoules per mole. All right, but S is an octamer, and so it is S8 for the molar mass. Again, the negative is where most people will miss this. All right, so if you do not have the negative, you will have the wrong answer, because delta H being positive or negative, that is a big part of the question. Is this endothermic or exothermic? Well, it is exothermic. If I do this, does it get hot or cold? I'm burning something. Obviously, it's getting hot. Anytime you're doing a combustion, if you don't get a delta H as negative, you better double, triple, quadruple check. I only know of one example where this is not a negative value. So the other 99.999% of them are negative. So combustion is almost always negative. All right, so then we're going to use Hess's law. So you're going to, when you add reactions, you add delta H's. All right, so that is going to be manipulating your thermochemical equation. Now, if I go back here, which is interesting, so this is your thermochemical reaction. Now, the answer that I had before, here is a better answer for what I had before. The wrong way. All right, and here. If I wanted to give this balanced chemical reaction and I wanted it for 1S, I would say 1/8 of S8. All right, so if I just divided this whole reaction by 8, I would then divide the delta H by 8. And so that delta H would be negative 299 kilojoules per mole. All right, so if I multiply through a reaction by a factor, if I multiplied by 1/8, I have to multiply the delta H by 1/8. If I multiply by 8, I would have to multiply the delta H by 8. All right, so that is manipulating your thermochemical reaction because this is per mole. All right, and this is when you have your negative 2.39 times 10 to the third, that is per mole of S8. If we had 1/8 of a mole of that, well, then we have to take that 1/8 of that number. And so 1/8 of that number is negative 299. So when you manipulate your thermochemical equations, when you multiply by a factor, all right, the factor can be 2, 3, 4, 1/2, 1/3, 1/4. You have to multiply the delta H by that same factor. When you reverse a reaction, all right, so if you reverse a reaction, the sign of delta H is reversed. So if I had SO2 goes to 1/8 of an S8 plus an O2, now my delta H for this is positive 299 kilojoules per mole. Right? So, because if I had 1/8 of S8 plus O2 gives SO2, I just did that one. That is my delta H is negative 299 kilojoules per mole. All right, so when I reverse it, if your reactants become products, products become reactions, you have reversed the sign. If I write it in terms of heat, heat here is going with the SO2. So I'd have up here, I would have 1/8 of S8 plus O2 goes to SO2 plus 299 kilojoules per mole. All right, heat is released. Heat is a product. All right, if I'm down here, I would write 299 kilojoules per mole plus SO2 yields 1/8 S8 plus O2. The heat is up here, it is a product. When you reverse the reaction, the heat is a reactant. When your heat is a product, it is given off and it is exothermic. When your heat is a reactant, it is absorbed and it is endothermic. So your sign of delta H will tell you if it's endothermic or exothermic. Negative, exothermic. Positive, endothermic. You need to know that endothermic means that the heat is a reactant. You need to know that exothermic means that heat is a product. It is released during the chemical reaction. All right, we will pick up there on Monday.